Good morning. First of all, I would like to thank the organizers for giving me the chance to present my research. My name is. I, mean, I didn't select the talks. Yeah, my name is Samuel Sanchez Lopez. I am a postdoctoral fellow here at IMSC, and today I will present this recent paper that I wrote with my collaborator Jose, who is also a postdoctoral fellow in Portugal. This is an outline of my talk. I will first give brief introductions to scalar-induced gravitational waves and to Palatini FFR gravity. Then I will present the main results of our paper, which is basically I can't find the words. We set up a general framework for the study of scalar-induced gravitational waves in FFR gravity. And I will also show some example spectra. And I guess the main point I want to make is that the spectrum of scalar-induced gravitational waves is sensitive to modifications to GR, and these modifications may be tested by upcoming gravitational wave experiments. So to talk about scalar-induced gravitational waves, I have to talk about inflation, but because we've just heard a couple of very nice introductions to inflation, I will just say that it's a period of exponential expansion in the very early universe, which solves the horizon and flatness problems, and which provides a mechanism for the production of perturbations that source all structure in the universe. So I'm talking about perturbations. As you know, the universe on cosmological scales is very large scales, is very homogeneous and isotropic, but there is structure on top of this homogeneity, and the proper language to describe this is cosmological perturbation theory, which basically consists on expanding every quantity that you have, like your metric, your energy momentum tensor, and so on, in a background homogeneous part, plus a perturbation that depends on the coordinates. And for example, this is the most general perturbed FRW metric, where each of these perturbations, A, B, and C, can be expanded as a power series like this. And in cosmology, we usually truncate the series at 2. We usually work at first or second order at most. But the point of this slide is that at any given order in perturbation theory, different kinds of perturbations don't mix. So, for example, here I'm showing the evolution of the gravitational potential and of the gravitational waves. And as you can see, they are decoupled. And here I'm just showing the evolution of this gravitational potential during radiation domination. At superhorizon scales, it's frozen, and this can be connected to the primordial power spectrum from inflation. So at any given order, perturbations don't mix, but if you go to higher orders, you can have sources from lower orders. And in particular, I'm interested in tensor modes at second order, which could be sourced by scalar, vector, or tensor perturbations at first order. But I'm interested in scalars, and this is what scalar-induced gravitational waves are. After some math, you can find that the power spectrum of these gravitational waves is given by this integral, where u and v are momentum variables. You have this factor here, which depends on the polarization of the gravitational waves. You have your kernel function, which encodes the sub-horizon evolution. And you also have here basically the square of the curvature power spectrum from inflation. Actually, the observationally relevant quantity is this density spectrum of gravitational waves, which is related to the power spectrum in this way. And here I'm just showing some examples I took from Inomata and Nakada. For this example, log normal power spectrum, and for example, you can just focus on the blue lines. In dashed, you have the power spectrum, the scalar power spectrum, and in full, you have the associated spectrum for the induced gravitational waves. And why is this interesting? As you know, the power spectrum at C and B scales is constrained. It's about 10 to the minus 9. But at smaller scales, it's not. And in principle, it could be amplified. And if it's amplified, it could lead to the production of primordial black holes. And if so, it would inevitably lead to the production of the associated scalar-induced gravitational waves. And this is hopefully to be measured by upcoming gravitational wave experiments like all of these, LISA, SIGW, Einstein telescope, and others in the high frequency range, and the pulse timing arrays in the nanohertz frequency range. And if this were to be measured, it would provide a lot of information about the inflaton potential at like smaller scales and so on. But again, the point of my talk is that this possibly measurable spectrum is also sensitive to modifications to GR. Okay, so what modifications to GR did we consider? We just considered f of r gravity, which is, as the name itself says, is just a function of the Ricci scalar. And we did it in the Palatini formalism. What is the Palatini formalism? You take the metric and you take the connection and you assume they are independent. This doesn't mean you are introducing new degrees of freedom into your theory, like an extra scalar field or something. It's just a choice of what your degrees of freedom of the theory of gravity are. When you take the equation of motion of your independent connection, you find that it's actually the Levi-Civita connection, the usual connection from GR, plus this correction term here that depends on capital F, which is just the derivative of your initial F with respect to the Ricci scalar. And if you do a little bit more of work and you take the trace of your metric field equations, you find that capital F, and therefore also R, and therefore also small f, are algebraically related to your the matter fields of your theory via the trace of the energy momentum tensor. And for example, for this function here, r plus r squared, you find a similar law as in GR. Now you take all of this and you plug that in your metric field equations, and you find that you get basically your Friedmann equations, and you find extra terms, which are time derivatives of the f function, or in other words, time derivatives of your matter fields. So effectively, what this modified gravity does is it introduces additional matter sources to your Friedmann equations. But this is background, at the background level, and we want to do perturbation theory to second order, so we need to do perturbation theory to first order also. And yeah, I will not go into any detail. I just wanted to show that these are the Einstein equations to first order in Palatini f of r gravity. And this is one of the main results of the paper. This is the equation of motion for the second order tensor modes in this Palatini f of r. On the left hand side, this equation is very similar to GR. You just get this modified Hubble parameter. And on the right hand side, your source has the GR terms, which are the first line, and then you get these all other terms, which depend on F and its perturbations, which means that it depends on the matter fields and its perturbations. And this is general, like this is just no approximations are made. But to make progress and to obtain a specific spectrum, we have to choose one F, and we chose one of the most widely used and I guess better motivated examples, which is r plus r squared, Starobinsky inflation. And we studied the production of gravitational waves during radiation domination for W equals 1/3. The trace of the energy momentum tensor for a radiation fluid is 0. So if you go back to your trace equation, you find that the only contribution to the trace is the subdominant matter component during radiation domination. And to give you a taste of how things go, if you look at this capital F, it is 1 plus alpha, the density of matter, over m Planck to the 4. This F appears ubiquitously in all the equations. And here, basically 1 corresponds to GR, and then you have this modification. So this motivated us to treat, and this is obviously a very small number, so this motivated us to treat the modifications to GR perturbatively. So we expand every field, for example this field here, in its GR plus a modified gravity part, where the perturbative constant is given by alpha times the density of matter at present over m Planck to the 4. And this is a tiny number, 10 to the minus 121 times alpha. So alpha could be huge, and still we're fine in the perturbative expansion. Okay, so we expand every quantity, and in particular we also expand the kernel. And we find that the modified gravity contribution to the kernel is proportional to the GR part times alpha times the temperature overheating squared. And here I'm showing the solution, numerical solution to the kernel. In blue is GR, and in orange is the modified gravity contribution. For alpha equals 10 to the 67, but okay, this is huge, but if you multiply this by 10 to the minus 121, you're still fine. And okay, this is our main result. We computed the spectrum of scalar-induced gravitational waves for the same example curvature power spectrum that I showed you before, the log-normal law. And in blue is GR, and in orange is R plus R squared. We obtain basically a scale invariant amplification of the spectrum. So for every frequency, you obtain this boost. And what's interesting is that recently this other group, Kugaraja et al., did the same as we did, same setup, everything, except they did it in the metric formalism. And what they find is, again, blue is GR, and in red you have the metric formalism. So GR gives you something, metric formalism gives you something, modified gravity metric formalism gives you something else, and likewise for the Palatini formalism. So hopefully this can be tested in the future by all these gravitational wave experiments. And yeah, thank you for your attention.
Thanks, Samuel, and also for keeping in time. Questions?
Thanks, Samuel. Just, but the equations of motion will be the same in either formalism, right?
No, it's totally different theories. First of all, well, I don't have it here.
Why do you say it's a totally different theory? It's the same theory, but you are just restating them in a different fashion, arriving at the equation of motion in a different pattern.
So the reason why they're completely different is because one way to see it is this trace equation. Here, the matter, R and F and small f are algebraically related to the matter fields. In the metric formalism, here you have plus a Laplacian of big F. So the relation between F and the matter fields is dynamical. So it gives you like completely different evolution.
I understand. So couldn't you have just, during inflation at least, converted into, carried out, gone to the Einstein frame and carried out similar exercise?
Yeah, I don't see why not. Yeah.
Then you will get a result more like the other guys.
No, I think our results should be frame independent.
Okay.
Whatever happens to the dynamics that makes it different, I think it carries out, like it translates to the Einstein frame through the couplings to the energy momentum tensor in some way. Like,
Okay, I'll
yeah.
speak to you later.
Sure.
Thank you.
So I have a very nice question. So in the affine connection itself, you are adding a new term. So is it guaranteed that for all such scenarios, this scalar vector tensor decomposition theory holds, or there can be theories where the evolution of these different perturbations can be coupled to each other?
So I'm not adding this. This just comes out of just varying the action. The mixing between different types of perturbations, yeah, they're independent. We showed that.
Okay, thanks.